I added one word to the name of my presentation. It's weak sandstone. In a few minutes you will understand why I did this. So I'm involved in the ground control movement of several coal mines in the Kuznetsk basin. So this is in the middle of Russia, near the Kemerovo region. And in the beginning I will say a few words about this, then show you the experimental results and the boundary value of problem formulation, and then the results of the numerical simulation. So if we take a look at the map of Russian Federation, here is Moscow, here is Kemerovo region, and this is basically the location of Kuznetsk coal basin. If we take a look at the conditional division of this basin into exploitation district, and it is shown in the graph, and this is a typical borehole log of a Kandomsky exploitation district. As you can see from this borehole log, many roofs of coal seams. Here you can see these black lines. These are the industrial production coal seams. And almost all roofs of these seams are composed of sandstone. And when the coal extraction begins, what is going on? The hanging roof appears, and at some spans of these hanging roofs, the collapse occurs. It means that we have to somehow understand the fracture behavior of the sandstone specimen. So this is like a final aim of the work, to build the mathematical model which gives you an opportunity to describe this fracture process of the sandstone specimens. And of course other rocks also, because they maybe have different physical mechanical properties, but they obey some general trends of mechanical behavior. So recently Farah-Cruz et al. Reported the data on the uniaxial compression strengths of a sandstone depending on the different pore content. And as you can see, the scatter is awful to my mind, because you can have a discrepancy of the data plus minus 100 MPa at the same porosity. This scatter is obtained data collected from, I don't know, maybe more than 1,000 specimens around the world from different deposits, sandstone deposits. In the Kuznetsk deposit, as you can see, we have pretty weak sandstone. If we plot this data on this scatter, then it will be right here in the lowest part of this scatter. And but discrepancy of data is not very high, so we can basically approximate this with the exponential curve. And what is going on? Basically, the sandstone and rocks, they poorly can have the tensile stresses inside of the material, but still, never mind. The uniaxial compression tests are the most usually used for investigation of the rock mechanics behavior, of rock behavior. And what we should account for? The first step, we have to account for microcrack closure in the case of a positive pressure and microcrack opening in the case of negative pressure. The second one, we need to more generally account for the pressure sensitivity of these materials. The next stage, we have to account for the dilatant behavior. We have to account for structural impurities, pores basically, and the next one, we have to formulate the yield of failure envelope, and then account for accumulation of damage, and what is more important, the corresponding degradation of the physical mechanical parameters. Hoek and Martin recently reported this schematic loading diagram. In the beginning, as you can see, there is the non-linearity, which is related to the micro-crack closure. So this is basically the first stage of simulation. Somehow we need to describe this process. And here in the slide you can see this initial non-linearity, and right in this point, approximately this micro-crack closure is finished. So this is like a multimodal theory, nonlinear elasticity, and one of the effective ways to describe this process is to account for the change of the bulk modulus of the material. So here, this is the current pressure, this is P0, it's the level of hydrostatic pressure when the microclosure occurs. And this is the phi parameter, it's the volume of microcracks which is closed under the certain hydrostatic pressure. That's what we have. If we use this equation, we can describe this initial nonlinearity. And here you can see the values of the parameters which I used in simulation. The next one, basically this is elastic region. It is not very interesting to my mind because nothing happens at this stage. It's just described according to the Hooke's law. And the more important part begins from the initiation of crack, which is basically 40 or 60% prior to the peak stress. And so the next stage of simulation, we need to describe the initiation and propagation of cracks. So how are we going to do this? As I said, we have to build the yield envelope, and as it is known that rocks basically obey the pressure-sensible behavior, that is why one of the suitable models for description of their behavior is the Drucker-Brage yield envelope. And we also utilize the non-associated flow rule, because experiments show that the dilatant factor and the internal friction factor, they both basically do not coincide. What is next? If we take this non-associated plastic flow rule, it is written in this way. So if we derive this equation according to the basic equation of a theory of elasticity, then we get the increments of components of inelastic strains. And we have the increments of inelastic strains intensity and the increment of dilatancy. So somehow we describe this process. What is next? First of all, the material could not experience the infinitesimal expansion. That is why the dilatant factor and internal friction factor could not be lived as the constants. They need somehow to evolve during the deformation. And for the sake of simplicity, I use this, the exponential dependencies. And if the accumulated intensity of inelastic shear strains reaches the critical value of with the star, then it means that the dilatant factor and internal friction factor decreased by E. So, and it is referred to this very good review by Alejandro and Alonso. They picked up the experimental data on different rocks, and it proves that these factors could not be lived as the constants. The next one is we have to account for the damage accumulation, which causes the degradation of cohesion of the material. And in this work we used this simple equation. Later in the line I prepared a few more slides. If you have a question, I will not stop here because I don't have much time. So the next one is the structural impurity, and also what we can take a look at this publication. This is one of the also reviews recently reported by Jean, and what they found, they looked through different dependencies of the pores, and basically they obey the log normal distribution. If we, of course, we didn't focus on the same like deposit of the sandstone as Jean et al., but this is like general law. The pores are distributed according to the log normal law. If we take into account this distribution diagram and then use the pseudo-random number generator, then we can generate computer-based, so computer-aided design of the internal structure of the sandstone. If we use this diagram, then we can put to have this structure generated and then use it for simulation. Of course, this is like a model because basically the pores, they don't look like, sometimes they look like spheres, but sometimes they have more like complex geometry. but for modeling it's fine. And if we take a look at the actual compression of this, we performed like a test simulation on this structure. It has approximately 12% of porosity, and as you probably know, the real condition of loading lies between the free sliding and the confined sliding. So we performed both, and as you can see, in the case of confined sliding, the fracture process is more controlled by the shear strains. So the tensile cracks also we have a final failure pattern, but I would say that it's more controlled by the shear plastic strains. But in the case of a free sliding, we generally have more like tensile stress, so it is more controlled by the mode 1 fracture pattern. And finally, then for the following simulation, I decided to stop on that one on the free sliding because, to my mind, it was more representative, as if we can say so. And if we take a look at the stages of deformation, the first one, as I already said, this is the micro crack closure. The second one is the initiation of the cracks. This third one is its initiation of the softening region, and then we have the coalescence of cracks and turn to the residual strengths of the material. If we compare these stages of macroscopic failure, macroscopic loading diagram is the fracture patterns corresponding to these points, then we will see this here. It's the B stage when we have the initiation of cracks. Then we have a stable crack propagation, and here in the beginning of a softening region, after that we have the unstable cracking and coalescence of cracks into the macroscopic one. Then again, if we use this pseudo random numbers generator, we can simulate different pore content and perform the same uniaxial compression test. And we changed the porosity from basically from 1%. There is no here this diagram, but here from 6% to 25 approximately. Here you can see these principal loading diagrams, and what we did, we took these values of the peak stress, and yes, here you can see this magnified window to see that we have a decrease of the elastic models, the Young's models, with the increase of porosity. And if we scatter all this data on the same diagram which I showed for one of the first slides, then you can see that the model gives a satisfactory agreement of the numerical simulation data with the experimental one, approximately in this range from 5 to 25% of porosity. This point lies a little bit out of range, but we never get in the model the perfect correspondence of the simulation and the experimental data. But what is next, what is more important to my mind, again, that if we take a look at the peak deformation, not only peak stress, but peak deformation, then we will see that the increase of porosity leads to the more viscous behavior of rocks, because this critical strain appears to be more high in the case of the porosities higher than 20%. And few slides and I finish. Okay, so if we plot this, the dependence of Young's models on porosity, it is pretty well described by the exponential function, and the dependence of the uniaxial compression strengths on the Young's modulus. Here it is, I've received the results that is described by the polynomial function of the second order. Basically, sometimes it is described by the linear, so it depends on some conditions. Yes, and one more thing I wanted to show you. There is a simulation of acoustic emission. If we calculate the counts of fracture, then we will see that the most high rate of energy release we get on this downfalling part of the loading diagram. Then when we have returned to the residual strength, this energy release rate basically decreases. And here I've also prepared a short dynamics of the damage accumulation. So take a look. Yes, there are not so many frames, but still take a look at the dynamics of this process. So we propose to the conclusions. We formulated the finite difference model of uniaxial loading of porous sandstone specimen, validated the model parameters by the experimental and literature data, and the model under development gives a satisfactory agreement of the numerical simulation results with experimental data, and the structural impurities play a crucial role in the fracture process because they are responsible for the occurrence of tensile stresses in the regions where the curvature of internal structure changes. So basically that's all what I wanted to tell you. Thank you for the attention.